Lewis dot structures for simple molecules following some very straightforward steps or procedure. We're going to do two examples in this video. The first is going to be formaldehyde, carbon, 2 hydrogens and oxygen, and then we'll do a second example of the nitrite ion. So the first step you want to look at is how many valence electrons do I have in the molecule. And so carbon will have 4 valence electrons. It has 6 total, but 2 of those are the core electrons in that 1s orbital. One of the easier ways to do this is to look at the group number for the element in the periodic table. But however you get about it, carbon should have 4. Hydrogen has 1. But there are 2 hydrogen atoms, each providing 1 valence electron. We need the total valence electrons for all of the atoms. And oxygen provides 6. So when I draw my Lewis structure for formaldehyde, I need to include a total of 12 electrons. Second step is the correct skeletal structure. And you're going to generally put the least electronegative atom other than hydrogen in the center. Okay, in this case, that's going to be carbon. Hydrogen is never the central atom, and that's because it can only take 2 electrons. Carbon is more electronegative than oxygen, less electronegative than oxygen. So oxygen and hydrogens will then be placed around carbon, around the outside. Okay, and it doesn't matter where you place them. I've placed them here. If you drew them in different positions, it doesn't matter too much. The Lewis structure on its own doesn't give you the shape. It's just going to give you connectivity. And now we're going to start putting in electrons. And we start with single bonds from the central atom to these peripheral atoms or terminal atoms. And then we come back and we start putting lone pairs on the peripheral atoms. So we have 12 electrons. I'm going to count up to 12. Each single bond is 2. So 2, 4, 6. And now I'm going to put electrons on the peripheral atoms to give them octets. So each element is going to desire to have 8 electrons. They get 2 shared electrons from that single bond, and we want to add electrons from our pool. We can only go up to 12 to fulfill those octets. Now hydrogen are different. Hydrogen take 2, or a duet. Each of these hydrogens already has 2, so they're set. So I'm going to put my 7, 8, put them in as pairs, 9, 10, 11, 12 on the peripheral atom. If you still have electrons after you've taken care of all the peripheral atoms, then you go to your central atom and add more. But in this case, even though carbon needs 2 more electrons, it has 2, 4, 6 electrons all shared. It needs 8. I should not have drawn those as doubles. Okay, so it's too short. It doesn't have an octet. And that's where we form octets for those central atoms by taking electrons from the peripheral atoms. I'm going to take these 2 electrons and move them so that they're shared with both the oxygen and the carbon. And so I'll erase them and then draw it as a double bond, a second line parallel and next to that first line. Now that oxygen shares 4 electrons, 4 bonding electrons, and has 4 non-bonding electrons. That's a total of 8. The carbon shares 4 bonds, or 8 total electrons, with other atoms, so it has 8. Both have an octet, have 8 electrons. And so that's the Lewis dot structure for formaldehyde. So remember, hydrogen is never the central atom, and hydrogen only gets 2. You can't give hydrogen more than 2 electrons. There's only 2 electrons in that 1s orbital. Okay. Ions behave a little differently. We're going to still start by determining the total number of electrons. The nitrogen should have 5 valence electrons. Each oxygen, there's 2 oxygens, each should have 6 valence electrons. But in addition to those electrons, valence electrons from those atoms, we have a negative charge. And that negative charge is going to add 1 more electron. Now, some students mix this up and they think negative, I should subtract. Having more negative charge means you have to have more particles with negative charge on them. That's more electrons. More is plus. So if you had a cation, a positively charged ion, you would subtract the charge. If I had a 2 negative ion, I would add 2. If I had a 2 positive ion, I would subtract 2. Okay, so in this case, I'm going to need 18 electrons. The least electronegative atom, in this case, is nitrogen. I'm going to go ahead and put that on the inside, and I'll put the oxygens around the outside. Again, it doesn't matter exactly where you put them, but nitrogen is going to be your central atom. I'm going to draw single bonds to nitrogen as my first step for adding electrons. That's 2, 4, and now I'm going to go around the peripheral atoms. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now I haven't gotten up to my 18. Now that I've taken care of all the peripheral atoms, I'll go ahead and put them on the central atom. So 17, 18. Okay. I've now added all of my electrons. I can't add more. I can't put 2 more electrons down here on the nitrogen to give it an octet. I have to come up with a different way of doing that. Now in this case, I have 2 oxygens I could potentially pull from, but I'm going to get that central atom to have an octet by removing 2 of the electrons from one of the peripheral atoms so that they can be shared with the central atom. Okay, so here is a Lewis dot structure for the nitrite ion. Because I have an overall charge, I'm going to put that whole Lewis dot structure in brackets and give it a -1 overall charge. That doesn't tell me where the charge is located in the ion. It just tells me that overall there's a single negative charge. Now the second issue I have is that I could have just as easily drawn the Lewis dot structure so the double bond went to the other oxygen. And this is a second Lewis dot structure for nitrite where each atom has an octet. Okay. These are going to be equivalent in energy. We'll talk about that a little bit with the video on formal charge. But these are going to be equivalent in energy. And I'm going to represent these two as resonance structures. Now reality is somewhere in the middle. Double bonds tend to be shorter than single bonds. But in the nitrite ion, both bonds are the same length. And they're somewhere between a double and a single bond. So the truth lies somewhere in the middle of this. Another interesting thing to point out about this is while I've drawn the nitrite ion in a straight line as a linear structure, the real shape of nitrite is bent. It has an angle of about 120 degrees between the 2 oxygen bonds. Okay. Keep in mind that when you draw Lewis dot structures, you're just looking at connectivity of atoms. You need to look into the VSEPR model to start talking about molecular shape.